Hello and welcome. This time we are going to go and expand on the topics that we had learned in the first part of regression. As I told you in the end bit of regression part 1, this time we're going to look at a little bit more trickier bits of working with regression models. As you've seen that there are certain things like outliers and influencer points, and the ones in which we want to take care of the uncertainty around our beta parameter estimates and the slope parameter estimates. How do we do this? How do we know that certain things are outliers and they're going to distort the relationship, such as they're the ones that are influencers? So those topics will be dealt with in this particular module. We will start taking a look at the outliers and influencers, and then we'll start taking a look at how you can draw 95% confidence interval band around your slope line. This is really going to be very, very useful and helpful for you, not only for learning the two variable cases, but as we expand and go with multiple variable situations, you will really make use of these modules. So pay close attention to the processes. Thank you, and let's get learning. In this particular set of lectures, we are going to talk about the outliers and influencers that are important for linear regression. So this is linear regression part 2. In part 1, we discussed if you have got one outcome variable and one explanatory variable, both of them being continuous, then some of the preliminaries of how to graph the two variables, how to introduce a fit line, and some of the other features that we had discussed. In this particular set of slide decks, our interest will be around outliers and influencers. What are outliers? Well, for both explanatory variables as well as outcome variables, in real life, you will find that several data points can be such that they will have some natural variations around an average value, but some data points will be so far out that they almost seem that they do not belong to the rest of the point cloud that you get to see. For single variables, for example, we use a box plot where you can see that some values which lie beyond the whisker marks are the ones that are labeled as outliers. So in a sense, therefore, outliers are those data points that are outside of the normal expected range of the values of a particular variable. Out of those that are outliers, there are a few that will seem to influence the relationship between an explanatory and an outcome variable. So we're going to learn about them in this particular module. We're also going to see a few other things. For example, how we can build an expected zone, in other words, a confidence interval around both the beta coefficient as well as the regression line, and some other things. This is, of course, part of the ePathshala program, and my name is Arindam Basu. I'm at the University of Canterbury in New Zealand. You've known of these things. In general, the way we are going to work with this is that we're going to first introduce some of the core concepts. We'll talk about some principles. We'll do some demonstrations of some of the key principles, and then we'll summarize in the end for you to understand this. One of the things that is very important while we are at this is that this is not a very comprehensive account of the core principles of regression. For this, I recommend that you consult a standard statistics textbook or learn from others. Here, the focus is entirely on using R for these purposes. So while some of these concepts will be very familiar and you may already know this, the focus here is on using R for statistical computing in order to accomplish many of these tasks. So therefore, the objectives of this particular module are as follows. We shall learn, first of all, how to identify outliers in a linear model. Remember that throughout this course, we are talking about a continuous outcome variable and either continuous or discrete, that is either continuous or categorical explanatory variables
in isolation or in combination. And in this, you will have outliers, and therefore it is important that when we set up linear models, we need to identify the outliers that are present there. As I have already discussed, not everything is an outlier. There can be, I mean, not every outlier is an influencers, but there are some that are influencers. So we need to understand what are some of the influencers, or what are some of the influencing points in a linear model. And we shall also learn how we can build confidence intervals for slopes and predicted values and beta coefficients, etc. In general, in the previous sections, when we have talked about different kinds of data sets, we have resorted to learn from different data sets. Here, we're going to introduce a data set which is known as Wolf River dataset, and it is about presence of certain environmental chemicals in a river called Wolf River in the different depths of the Wolf River. And we are going to model the presence of aldrin and hexachlorobenzene in the different depths of the Wolf River. And these are the two variables that we are going to use. Both aldrin and hexachlorobenzene are continuous variables. So these concentrations are measured, I think, in terms of grams per liter, etc. So you will have a sense of, or milligrams per liter, and you will have a sense of how, they are mutual relationships. But this is only a talking point, to be honest. To give you a sense, here is the Wolf River pollution data set. We're only going to consider two pollutants, aldrin and hexachlorobenzene. And you see that the first variable is the depth in which they occur. We are not going to take into consideration this. And in this analysis, we are going to kind of model what is the variability of hexachlorobenzene with aldrin. It may or may not be too much of a meaningful issue, but at least it gives us a sense of running a simple linear regression for many of the things that we would like to follow here. Okay. So here is the code, and let me explain this code line by line. The first line is an object. So the first element in the first line is an object referred to as ALT-HCB. And then you see, as usual, we have done it before, there is, in this object, we store the product of a linear model, and this is stored in the form of a left-directed arrow with a dash, which is kind of a sign that says that we store it here. And then we store the product of a linear model, which is given by the combination of the letters L and M, which is linear model LM. And then we open a parenthesis and close a parenthesis. And in between the parentheses, we put a formula. This formula is known as Wilkinson-Rogers formula. And in this formula, on the left-hand side, we put the outcome variable. In this case, it is HCB, the concentration of hexachlorobenzene. And on the right-hand side of the formula, we put the explanatory variables. In this case, we have got only one explanatory variable, and that variable is referred to as aldrin, which refers to the concentration of the compound aldrin in water. The direction or the position of the outcome and the explanatory variables is very, very important here. You must always place the outcome variable on the left-hand side, then put a tilde mark according to the Wilkinson-Rogers formula to indicate that this is a linear model. And then on the right-hand side, you must put the explanatory variable. Then we put a comma. So this combination of the outcome variable tilde and the explanatory variable, that combination itself is a linear model. Then there is a comma, and then you put the data from where it is taken. So the data in this case is Wolf River data. This is how we store a linear model in the ALT-HCB. This is the beauty of R. As you can see, that in this simple object, we have almost everything that we need in order to produce things. So if we ever need anything that is to put any parameter out of that model, we can manipulate this object. In the second line, we create another object, and this object is known as SUMALD-HCB, so SUMALD-HCB. The SUMALD-HCB is an object, and in this object we store the summary information of the linear model. The linear model is stored in the object ALD-HCB, and this linear model, of course, a linear regression model, because linear model is a generic term for any regression model for that matter. Anything that has got a linear modeling can be put into this framework. So we put the summary information into SUMALD-HCB. Then we create another object, and the name of that object is ANOVA ALD-HCB, where we are going to put in this object, we're going to store the results of the analysis of variance of the linear model ALD-HCB. So we store the ANOVA results in ANOVA ALD-HCB. One of the first things that we do with any linear model or any data analytic process is we create a plot. In our case, as we have seen before, because our outcome variable is continuous and our predictor variable or our explanatory variable is continuous as well, therefore the plot that we plot here is a scatter plot. The command or the function that we use in order to plot a scatter plot in R is that we say it's a plot. Then we use a notation which is very similar to the Wilkinson-Rogers notation that we use for specifying a linear model. And here hexachlorobenzene, or the outcome variable, is placed first, which is on the left hand side. Then we issue a tilde mark, and then we issue the explanatory variable. In this particular case, that's aldrin. So aldrin is the explanatory variable. We specify the data, which is Wolf River, and then we write the main, which is the title text of the graph. The title text of the graph in this case is HCB versus aldrin in Wolf River. The plot itself is going to give us a dot plot of the different points that correspond with each other of HCB and aldrin, where HCB is the outcome variable and aldrin is the explanatory variable. But if you want some additional points to this, or additional information that we want to plot there, then we would like to plot an AB line, which is like a fit line. So we put a line which is referred to as an A and B line, which means that there is an intercept and a beta coefficient baseline. So that's why it's called AB line. And it's a linear, it's a line, so it's a line. And the AB line that we want to put here essentially is the ALD-HCB line, which is our plot line. So then R automatically figures out what is the best fit line, and it puts like that, and we specify a color, which is a red color. The resulting scatter plot with the fit line is here. As you can see that the fit line runs through the cloud of points that we initially specified in the scatter plot. However, while you are noting this, also note that there are 3 points, but definitely there's 1 point around the 6 to 7 mark in the x-axis, where you see aldrin, which lies quite far out from the remainder of the cloud with the points. Intuitively, by taking a look at this figure, you can argue that this solitary point could be an outlier. But this is not the only solitary point. There are 2 other points that we may also want to consider. Look in the upper right-hand side corresponding to the figures 8 and 9 on the x-axis. You can see that there are about roughly 3 points that you can pick up as potential outliers. In our next slide, we're going to take a regression summary and ANOVA. And you can see that in this particular case, the regression summary, when it prints out, it starts with a description of the residuals. And you can see that the residuals are fairly consistent. You can see that there is the median hovers around the 0 mark, but not quite. It's minus 0.11. And there seems to be some sort of a left skewness if you only go by the plotting of the residuals, but we'll not do that at the moment. Then the next block is about regression coefficients, which is also often referred to as beta coefficients. In the beta coefficient, because we did not specify that we wanted to remove the intercept, R will put the intercept term in, and here you can see that the intercept term consists of 2.62 as the unstandardized beta coefficient for intercept. It also prints out a standard error, the t statistics, and the probability estimate for the corresponding t statistic. And you can see here that it is the p-value is less than 0.005. It actually is much less than 0.001, so it's quite significant. You also see that the variable aldrin, which stands for the particular chemical contaminant that we're talking about in the river, it is also statistically significant. It gets an unstandardized beta coefficient of 0.52 with corresponding standard error value in it. The third block is where R puts out the residual standard error on the corresponding degrees of freedom, and then it puts out the F statistics and the R squared values. The R squared values, as you know from your studies, signifies the extent to which this explanatory variable, or the combination of the explanatory variable and the intercept term, can explain the variability in the HCB, or the outcome variable in this particular case. And you can see that it has got a highly statistically significant p-value, which shows that the model can explain the the model R square is not equal to 0. It's actually quite it can explain. The extent to which it can explain is roughly about 0.51. So going by the adjusted R square values, and it's roughly at 51% in the variability of the HCB, or the outcome variable, can be explained by this particular process. And then if we take a look at the residuals and the analysis of the variance tables, you see that this model is a strong explanatory model. We next move to what is known as the diagnostic plots for this linear model. And you can see in the four composite plots that we have seen put up over here, there are four plots. Going clockwise, the first plot is the plot between residuals and fitted lines. This shows that the relationship may not exactly be linear, may not be linear, but this is only one part of it. We also take a look at the normal quantile plots for the residuals. Again, you can see that there is some apparent deviation from a normal line, perhaps if one were to be drawn. And you can see that the square roots of the standardized residuals with the fitted values also show somewhat reversal of the pattern that you see between the residuals and the fitted values. And I'd like to draw your attention to the fourth plot, which is known as the Cook's distance plot, where you see the observation numbers and the Cook's distance that are being plotted. This reinforces what we had seen earlier. That is, earlier we had seen when we plotted the outcome variable with the explanatory variable and the fit line, we saw that there were 3 points that we suspected could be outliers. And here you can see that those 3 points, and you can get the numbers. So just to give you a very quick introduction to the concept of Cook's distance, Cook's distance actually measures the influence on the regression or the fit line if you omit a data point for every data point. So say, for example, in this particular data set, we have got 30 observations. So what happens if I remove an observation, and then we see that whether there is to what extent will the fit line will move around. And the one that will really move around a lot is the one which will be the one that is responsible for, it's quite a distance apart from the remainder of them. So then that is an outlier. One of the things with the outliers is this, that it enables you to identify whether an outlier is also an influencer. There is no real rule for this, but people therefore have devised their own standards at times. According to some, if the Cook's distance exceeds the magic value of 1, then for a particular data point, then that data point is an outlier. Other people have devised other kinds of ways in which you have to interpret the outlier and the distances as a result of this. So let's take a close look at the Cook's distance, and you can see that there are 3 outliers here. Observation numbers 13, 28, and 29. But if you go by the convention that the Cook's distance of 1.0 or more is a signal that this outlier is also influencer, then that does not work. And the reason why that does not work is because, you know, I mean, and because they don't work, you can argue that this is not really, may not be an influencer to some extent. So then the next question that we're going to ask ourselves is, what happens if I remove the outliers and rerun the models? Let's do this. In this particular case, what we have done, and let me walk you through the code, is now we have chosen to put the contents of the data frame Wolf River into another data frame. And this data frame is referred to as Wolf River 2. So Wolf River 2 is an object. And in this object, we have decided to store contents of another object, and that object is Wolf River. But we have decided to modify the contents of the Wolf River. And in this modification, we have decided to remove 3 rows of data. These 3 rows are 13, 28, and 29. So we have put them under C 13, 28, 29, which means that we have catenated the 3 rows. And in order to remove this, we have put a minus sign, so that the Wolf River will now, from the Wolf River, we are now going to take out these 3 rows. And we have subsetted the Wolf River in this way, which means in a subset, when you use a subset in R, there are 2 entities. One is you subset the rows, and then you subset the columns. Here we have subsetted the rows. In the second line then, which is quite familiar to you now, we have seen that we are going to store it into another object called oldHCB2, the linear model object. And then we are going to run the summary, the ANOVA, and the plot. So now we can compare the summary and the ANOVA plot between the original model and the model after removal. And here you can see that in both the models, the intercept is strongly statistically significant, but the intercept has reduced values or unstandardized beta coefficient for the model with fewer values, or the data points removed. You see that the Aldrin's beta coefficient has increased, and it has become stronger in terms of the p-value. You also see that the adjusted R-square for the new model is stronger than, or higher than, the adjusted R-square for the old model. And of course, both the models, according to the ANOVA models, they are quite significant. Next, we're going to take a look at the scatter plots along with the fit lines for these 2 models. On the left hand side, you see the HCB versus Aldrin in Wolf River in the old model with, with the 3 outliers included in this. On the right hand side, you see that the fit line has dropped down, so the intercept is smaller, and you can see that the slope is steeper than what you'd be expecting. So the intercept has become smaller and the slope has become steeper. So mildly, there is a change in the exact slope parameter for the new model, which is quite interesting. Which brings us to the other question as to whether we should remove or whether we should retain an outlier. There is no clear answer to this. The best thing that we can say is this, that diagnostic plots are not definitive. When we construct a diagnostic plot, particularly in trying to understand whether the regression line or the regression actually violates the core assumptions of any regression, and therefore we put plots for the outliers, we put plots for the residuals, we can get a sense of, there are outliers or there are influencer points. And what they actually point to is the fact that, they draw attention for further investigations. In other words, when we see that there are influential points, we would say that, look, these are influential points, so we have to be a little bit careful. We can't dismiss them. Let's take a closer look at this. If we would like to do something about them, the best strategy is to do what is known as a robust regression, which is a regression technique. However, we're not going to cover it, so I'm not going to talk about it anymore. But that robust regression is kind of resistant to the outliers and all of these other vagaries, if you will, of the distribution of the points. So that gives you a sense that there are sometimes uncertainties about point estimates and uncertainties about certain parameter estimates, and there are ways to address them. Next, we are going to consider another thing, which is about constructing confidence intervals, and this takes us back to the idea about the standard error that is reported in the model information. You can see that in any summary regression parameters that is reported, the software returns a beta and then a plus minus standard error. And because we rely on the t-statistics, therefore we have to use the t-statistic, appropriate t-statistic, in this particular case t for 0.975, and then multiply that by the standard error, and you can get a confidence band around this. So for the beta estimate or the regression estimate for both the intercept as well as for the for Aldrin, which in this case is the main explanatory variable, we can calculate the confidence interval band. And I've given you this. I've given you the code in the first line, ACB. And then you can see that we have stored the value of a function of a way in which we have extracted the coefficients from the sum alt HCB. Remember that sum alt HCB was the summary information of this regression. And from there we have extracted the beta coefficient for the second column and the second row. So the second row gives us the one for Aldrin, and a second column, so 2 by 2 basically means second row and second column. It gives us the estimates for the Aldrin, and then we have extracted the coefficient value for this. And then what we have done is this, that we have we're only interested in the coefficient, of course, and then we have constructed the values for the t distribution at 0.025, 0.975, and 28 is the degrees of freedom, and we multiplied that with the ACB. So you can get a sense that if you wanted to convert them into a confidence interval, what would we need to do? An easier way to use this is to use the inbuilt confint function. If you use the confint function, then you only need to type in the regression object, and it'll do it for you. Another thing that we would like to do is to do what is known as a graphs of the residuals and predicted values. And it is very important that in the graph of the residuals and predicted values, it's important that we plot the residuals and predicted values, or the fitted values. Almost never the independent variable, never the explanatory variable. That's number one that needs to do. The other thing that we need to do here is this, that when we have this fitted value, around that, then there is a case in which we can actually construct a confidence interval around the fitted value, and that is very, very important. So in order to do that, we first calculate what is known as phi hat, which is the predicted value of the regression, and then construct a confidence interval band, which also again will give us we can get that by constructing what is known as a hat matrix. So if you give this regression the outcome variable and the independent variable, then the program is going to put out a hat matrix, and from the hat matrix, which is the y hat, we can then extract the lower and the upper confidence interval based on the 95% confidence interval around the predicted value. And so we know that we could then put them using the lines function as on the graph itself, and you can do this here. So take a look at this fit line along with the confidence intervals, and you can see that the fit line along with the confidence intervals are plotted. So this gives us a sense of the fact that we can take a fit line and then we can put confidence interval around a regression equation very, very easily in R. So to summarize, in this particular module, we learned some more things about running regressions in R, taking only two variables, both continuous. That is, we learned how we can identify outliers. We learned that some outliers can be influencers, and we could find that out in R. And we also learned, quite vitally, that we could actually create a confidence interval band around the fit line, and this is going to help us to predict new values with new data sets based on the regression model that we have set up. So this kind of completes our first journey of learning about regressions and what we can do about regression model in R. So let's continue with the next module.
Now we are in a situation to take a big and broader look at what you have been learning all along. So in this two variable cases, you have learned that you can take two variables together at the same time. First, in the bivariate data analysis case, that you can take any two variables and find out their nature. That is, are they continuous variables? Are they categorical variables? You can pair them up. You can draw plots. You can start putting together what is known as a simple linear regression. And we just confined ourselves in these four modules that we had covered before, that is bivariate part 1, 2, and then regression part 1 and 2, two variables that are ideally continuous variables, how we analyze them and how we plot graphs, etc. So this completes our tour of the most important bits of dealing with the two variable cases. And what we are going to do now is going to focus on multiple linear regression, where it becomes really, really more interesting. All right, thank you.